Today we are talking about how we use embeddings to efficiently link alternative spellings of proper name strings. Record linkages with imprecise identifier representations is a very common task in business applications. One approach is to use a heuristic to compare permutations of the identifiers, but this may not be feasible in use cases that have very tight latency requirements. Our solution is to use doc2vec to create a single canonical representation of proper name strings in the embedding space that can be efficiently compared with candidates. There are many common variations of name spellings that can induce blind spots in our record linking algorithms. We consider these transformations to be a type of adversarial transformation. We analyzed a large set of successfully matched name variations, and from that manually built up a taxonomy of name transformations and formally codified them as Python functions. The table on the right shows the output of some of these functions on generated names. The first two rows display examples of spelling and order transformations, and the third row from the bottom shows a nickname as well as a spelling transformation. Lee and Mikolov extended Word2Vec to create doc2vec, an embedding model that creates a vector representation of an entire paragraph. Foxcroft built off of their work and actually applied it to the task of matching surnames successfully. The key intuition here is to understand that we are replacing paragraphs with proper name strings, and we're replacing words with actual characters. Our work builds on this body in three ways. First, we extend Foxcroft's work to evaluate multi-token names. Second, we codified these transformations and tested them both in the name matching task as well as in the training phase for the embedding model. And finally, we conducted a regression analysis to quantify the impacts of the transformations on the name matching task.
Now getting into the experiments. The data we used was completely synthesized from public name lists, and the diagram walks through how the data was generated. The important takeaway here is that we end up with matching pairs and random pairs for the test set, because the model is evaluated on name pairs. So given a pair of names, the model will classify whether the two names in the pair are matching based on the cosine distance between them. We also ran a linear regression analysis to see the effects of each transformation on the cosine distance. This would help us better understand the strengths and weaknesses of our model. First, we have the model evaluation. As a baseline measure, we used the Levenshtein distance to perform the same classification task, and it did very well with an accuracy of 97.8%. But our embedding model did even better with an accuracy of 99.1%. The bimodal distribution in the plot shows that the model can clearly distinguish between matching pairs and random pairs. One more thing to note here is that the baseline method was more aggressive than our model in trying to capture matching pairs. And that's why it has a much higher false discovery rate. Now for the regression analysis, the table shows the expected increase in cosine distance if that particular transformation was applied. We can see that the model is having some difficulty with nicknames, but what's more interesting is the ordering invariance, meaning that changing the order of a name has very little effect on the cosine distance. And this is a major advantage our model has over Levenshtein distance. We also included interaction terms in the regression analysis and found all their coefficients to be negative. This suggests that the effects of transformations are not additive, which is good for the model because applying more transformations doesn't scale the distance linearly. We have shown that embeddings work extremely well for linking adversarial name strings. But what's great about this approach is that it's not just restricted to proper names. It can also be applied to other identity elements like email or street address, as well as other applications in record linkage. This concludes our talk on name embeddings. Thank you.